All right, so yeah, thanks a lot, Stefan, for the introduction and for invitation to speak here. So the last topic of this week is going to be about, well, the title is Encrypted Quantum Computation, and more generally, this will be about cryptography and tools for the quantum cloud era. Okay, so we'll see what I mean by that. You know, we've spent the last 2-3 days talking about, well, really the whole week, talking about the threat of quantum computing on the one hand, and also, you know, how we can, you know, once this technology becomes available, how we can actually use it in constructive ways. But it's still basically an open question if and when and to what extent quantum computers will be useful. Okay. But you know, there's been a lot of progress, a lot of resources being put into building quantum computers. In particular, there was this, this made news in 2019 when Google announced that they had built a quantum computer that somehow solved a task that they claimed could not be solved by the world's best classical supercomputers. Really, they just, you know, put together a bunch of random quantum gates and kind of sampled from the output distribution of that quantum circuit. And they claimed that this is something that couldn't be done by our best classical computers, and so thus they've achieved what they call the quantum supremacy. Okay? This was like very soon met with some backlash. Like almost immediately, IBM said, no, I mean, like probably we can simulate this on classical supercomputers if we work hard enough. And so this brings up the question, right? Like, if we're gonna, you know, is this like kind of back and forth inherent? Like, how can we actually verify that, you know, Google did something really kind of truly quantum, something that we don't believe could be efficient classically, right? And the most like basic question here would be, how can Google or another entity with a quantum computer actually prove to the rest of the world, say like prove to us who all just have classical computers, you know, that they did something really quantum, right? And if they can provide a convincing proof of this, then we call this a verifiable quantum advantage. And you know, to this day, we don't really have such a verifiable, we have not seen such a verifiable quantum advantage yet, okay? So that's one problem. Now suppose, you know, fast forward a couple years and we have achieved quantum advantage, and so we have some useful quantum computers doing interesting things. Another issue that is, you know, already the case is that building these computers is extremely costly, it seems, and requires a lot of resources and concentrated expertise, right? Which means, like, in the near term, at least for the next, you know, for the foreseeable future, this technology will probably be highly concentrated, and we're already seeing this, you know, big companies like Google, IBM, and Amazon will, you know, be the ones that will be kind of like running this quantum technology, and it will probably be a long time before, you know, the rest of us just have like quantum computers lying around, right? So what that means is that this will be a really common scenario for the foreseeable future for how we interact, for how the world kind of interacts with quantum computing, right? So there'll be this notion of a quantum cloud administered by, say, Amazon or Google or IBM. And then if we want to take advantage of a quantum computation, then, you know, we would imagine just, you know, sending some description of a quantum program that we want to compute to the cloud. So here, you know, I'm imagining there's a classical client that sends the description of a quantum circuit. Say this can be just a classical description of a instructions for how to compute some quantum program, along with some input X, and sends this to the quantum cloud. I'll refer to the description of the circuit as Q throughout this talk. So Q is going to refer to some description of a quantum program. And then, you know, we'll ask the quantum cloud to evaluate the program, and we'll expect a response, right? So it seems like this will be a really common you know, way that we will be interacting with quantum computers. And so this brings up the question of, what sort of security properties could we hope to guarantee for the classical client in this setting? And one really basic one is this notion of privacy or blindness. So let's say that the classical client wants to perform some quantum computation, but they don't want to tell the cloud, say, what input they're running this quantum circuit on. Okay. So this is called blindness. Basically, we want to outsource the quantum computation, but we don't want the cloud to learn what computation or what input we're running. Okay. And then the other, maybe most natural one is the notion of authenticity. Okay. So the client might want to, ensure that the value y returned by the quantum cloud is actually the output of the quantum computation that they asked, right? For example, like as I mentioned, quantum computing seems to be pretty costly. So, what if the quantum cloud is just kind of pretending to be quantum and actually just executing something classical to save money and just trying to like dupe the client into thinking they really ran the computation, right? So, we might want to design a way for the classical client to ensure that their output was correctly computed. So this talk is going to be about all of these notions, like proofs of quantumness, blind quantum delegation, verifiable quantum delegation. But most of it is going to be focused on this notion of blindness. And the reason is really that the techniques that have been developed to ensure blind delegation will also be relevant and be very useful for designing these more verifiable schemes. So I'll probably spend most of the time on blindness and then show at the end how these techniques can be used to achieve also proofs of quantumness and verifiable delegation. Okay. So then, given that, the plan will be roughly as follows. So I know there's already been a couple days of quantum talks, but I want to start with, again, some quantum background to cover some aspects of quantum information that will be particularly useful for this talk. Okay? And then I'll tackle this question of blind delegation. So again, outsourcing quantum computation to the cloud without revealing what input we're running the computation on. And so we're going to first show how to reduce this very general problem to something that I'll call oblivious state preparation. It's a much easier problem to think about. And then we'll show how to achieve this kind of building block using post-quantum crypto. In particular, we'll show how to use just the LWE assumption to achieve it. And then finally, this gives us our blind delegation. And then in the last part, we'll show how these techniques can also be useful, as I mentioned, for verifying quantumness. Okay. Yeah. So any questions before I get into that? Okay. So yeah, I'll spend a bit of time on just some quantum background first. In particular, before we understand how to do blind quantum computation, we'll at least need to understand how to encrypt quantum states, right? Because like the intermediate states of this computation will, in particular, be quantum. The server will be running that, and we'll at least need these states to be encrypted, right? So we'll cover how to encrypt quantum states. And then the other really crucial building block will be quantum universal gate set, which has been mentioned a couple times before. But this is going to be a way to take our computation and break it up into smaller pieces so we can deal with each separately. Okay. Okay. So I want to first start with a way to visualize single qubit states using the block sphere, which in my opinion, is like an extremely useful tool for intuition. And so if you've seen it before, this will just be a review. But otherwise, I think this is something that, like, even independent of the rest of this talk, is something good to know. So we've known since Julio on Wednesday that a single qubit state is well, just nothing but a two-level unit vector in complex space. So a single qubit psi can be written as alpha 0, 0 plus alpha 1, 1, where alpha 0 and alpha 1 are complex numbers, and this is normalized, okay? But how do we start, is there a better way to visualize this than just like thinking about two complex numbers? I mean, we could start by just writing down, a complex number alpha 0, I can write it down on the complex plane. But then I'd also have to write down alpha 1, and suddenly we have like 4 dimensions that we're playing with, right? So an easier way to visualize a single qubit is as follows. So first, let's recall that any complex number can be in particular represented as a norm, okay, R0, like a length of the vector, as well as an angle, so like how much that vector is from, let's say, just the real axis, right? So let me just write my state in this way. So this is like also called like polar form, right? So I'll write alpha 0 as R0 e to the I phi 0, alpha 1 as R1 e to the I phi 1 for 2 angles phi 0, phi 1. And then what I can do actually is I can factor out this so-called global phase. So I'll just divide everything by e to the I phi 0. And you can kind of confirm that like this term here, this is just like a norm 1 complex number that just kind of multiplies the entire state, is something that's not really physically relevant, right? Anyway, I measure this state, or I compute on it. You'll see that the presence of this global phase doesn't actually affect the results that I get. So I might as well forget about it, okay? And so now I can write my state in this form, where the phase is just on this one vector, okay? And then the final thing I can do is to say that, well, I know that this state has norm 1, and so in particular, these real numbers R0, R1 must be such that R0 squared plus R1 squared is equal to 1. And so really there's only one parameter defining R0 and R1. It's kind of the ratio between them, okay? And I can write that parameter using an angle theta, okay? So as theta ranges between, as theta over 2 ranges between 0 and 90 degrees, that kind of gives me the ratio between R0 and R1, okay? So actually what I've done is I've taken any single qubit quantum state and written it using just 2 parameters, this angle theta, okay, and this angle phi, okay? So basically, again, like theta represents like what is the ratio, but like, how biases the state towards 0 versus 1, okay? And then phi is a parameter which is, sometimes just called the phase of the state. It kind of represents, essentially how far this state is kind of rotated around the sphere, okay? So just to be clear of the notation on this block sphere, right? The plus state refers to 0 plus 1, minus is 0 minus 1, minus I is 0 minus I1, plus I is 0 plus I1. And actually, technically, these should be all divided by root 2, but the convention for the rest of this talk is that I'm generally just not going to write normalization factors because they'll usually just be clear from context, okay? Okay, so after doing all of that, what we've derived is that essentially any single qubit state, I can represent it as a point on this unit sphere, okay? And any point on the unit sphere can be specified by these 2 angles, right? Theta and phi, okay? And moreover, any single qubit unitary, so any operation I apply, a unitary operation to a single qubit, will in particular just be a rotation of this sphere, okay? So I can think about, arbitrarily rotating the sphere as just some, quantum operation that takes psi and outputs another psi, okay? Good. Any questions about this? So this is just a really useful way to kind of visualize what is a single qubit state. Okay. And now we can think about what are the most common operations on single qubit states. And so let me start with something called the Pauli rotations. Okay. So let's start with the bit flip operation. Okay, so the bit flip operation is called X, and it's basically just a 180-degree rotation around this X-axis, what I labeled in yellow here. Okay, so we can see that if I perform a 180-degree rotation around X, I will, map the 0 state to the 1 state, and I'll map the 1 state to the 0 state. So this is really just like flipping these bits, right? Now, I could also define an analogous operation, which is called the phase flip operation, or capital Z, which is just an 180-degree rotation around the Z-axis. Okay, so this is going to map the plus state to the minus state to the plus state, and it will keep 0 and 1 fixed. Okay, so there's also like the Y Pauli rotation, but we usually don't talk about that. It's, I mean, the reason really is that you can derive it just from X and Z. So like if you want to get a rotation on the Y-axis, you can basically multiply X times Z, essentially, up to a global phase. Okay. Okay, good. So these will be like, these are the X and Z rotations are like two like really basic, really common operations in quantum information. Okay. So with this, we can understand now how can we actually encrypt a quantum state. Okay. So let's start with recalling how to encrypt classical states, in particular the classical one-time pad. Right. So kind of the most basic way to take a bit and encrypt it is to just sample a random bit R and output B XOR R. Okay. So this is kind of the encrypted version of B, and R is the secret, right? So I can write this classical one-time pad using my quantum notation. And so, on this block sphere, the two classical states are 0 and 1, right? And so I can just write that as like a ket B. And now the classical one-time pad, what it's doing is it's like, sampling a random R. And based on R, it's either applying a bit flip or not. Okay, so I can write that operation as X to the R times B. So if R is 0, I do nothing. I just keep B where it is. If R is 1, I apply a bit flip, which flips between these two states, right? And so one way to visualize, I mean, it's, this will be building up to the quantum one-time pad, but one way to visualize why, like, intuitively this is secure is to say that, well, if I know that my state that I'm starting with is a classical state, it's either the 0 or the 1 state, and the result of this one-time pad is to basically, with probability 1/2 output 0 and with probability 1/2 output 1. And if I average together what I get, I can literally take like an average between these two states, and you'll see that I get a state at the very center of this sphere. Okay, so we haven't really talked about mixed states this week, and I won't really like formally define anything. But the intuition is that I can take any probability distribution over single qubit states and write that as a mixture of those states, an average of those states, which I can represent as a point on the interior of the sphere. Okay, and so the fact that, like, if I average 0 and 1, I get a point at the very center is telling me that, like, this is a maximally mixed state. It contains the middle of the sphere contains no information about what state I started with. Okay. Yeah. Good. Yeah. So yeah, the question was, 0 and 1 are orthogonal, and usually you'd represent these at like a 90-degree. Is that the question? And so why are they? Yeah. So this is, I guess, if you. Yeah. So here, I'm kind of like expanding the angle. Like I'm just kind of defining the angle between 0 and 1 here to be pi, or pi. Sorry. Good. I'm defining the angle between 0 and 1 here to be 90 degrees. So actually pi over 2, but I'm kind of just like multiplying everything by 2. That's what I'm doing. So so good. You should indeed think of every kind of 2 points that are opposite on the sphere, like 0 and 1, plus or minus, or like any two kind of opposite points as being orthogonal. Okay. Does that make sense? All right, so this was our classical one-time pad. The problem is that this doesn't really, yeah, so one way to think about what's happening here is we're basically, the one-time pad is essentially encrypting or hiding all information about the angle theta. The angle theta is telling us how close is the state to 0 or 1. And so if I just take a classical one-time pad, I'm kind of completely masking out theta. But it does not mask the angle phi at all, right? Like if I applied the classical one-time pad to the state psi, I will kind of average out information about theta, but I will retain information about phi. So like if I just try to apply the classical one-time pad to psi, I'm not going to fully encrypt that state. Yeah.
Once again, repeat like this inner. Yeah, I just want to make sure I understand it. Like this inner sphere, what was it representing? The mixed states.
Oh yeah. So I guess I should. This is not this is not a sphere. It's just meant to indicate this this central point. And so this is a good. So I can take a probability distribution over any two pure states. And if I take, with 1/2 probability 0 and 1/2 probability 1, I can average them together and I'll get the point at the center. And that's something called the maximally mixed state.
Oh, so this sphere is, you were just trying to say that you're trying to hide theta in this sphere somehow. Okay.
Yeah, sorry. This gray sphere maybe should just be like an arrow pointing at the point at the very middle.
Yeah, fine. I thought it meant to signify something more.
Yeah,
so.
yeah. Okay, so in 2000, it was shown, I guess, Mosca, Tapp, and DeWolf showed how to extend the classical one-time pad to the quantum one-time pad, okay? And, like I said, now any single qubit state is has these two parameters. Like a classical bit just kind of has one parameter, is the state to 0 or 1, A quantum single qubit state really has these two parameters, theta and phi. And so to fully encrypt a single qubit quantum state, we're going to need to sample two random bits, R and S, okay? And then based on S, we will either apply a phase flip or not. So this Z phase flip is what is going to, encrypt this angle phi. And so one way to, this is a little bit hard to visualize, but this will be kind of just like a proof by picture in some sense. So if I take any arbitrary state psi, my quantum one-time pad encrypted version of psi is basically in one of 4 possibilities based on these 2 bits R and S. So I can kind of compute what are the 4 possible states that I get from applying this operation. And again, if I start with any state on the sphere, and I average together these 4 possibilities, I'll again get the state at the very center of the sphere. So this is kind of a geometric way to see that, no matter what state I start with, the quantum one-time pad is a perfect encryption of that state. Okay. And again, you can think about this as, not just encrypting theta, but also encrypting the second parameter phi due to now the presence of the phase flip as well. Okay. And then finally, this, the intuition here is coming from just single qubit states, but you can just extend it to n qubit states. If I want to take a n qubit state psi and apply the one-time pad to it, I can sample 2 n-bit strings, R and S, and then I can apply, the ith bit of R and the ith bit of S I can use to define the quantum one-time pad on the ith qubit of psi. And so I can kind of compactly write the encrypted version of psi as x to the r z to the s times psi. Okay, is this okay? Okay, good. So this is how to encrypt quantum state. That was kind of the first main thing I wanted to cover in the quantum background. The second thing is a universal gate set. Oh yeah? Mm-hmm.
Maybe this will become a part later in the talk, but I'm wondering if there are limits to how you can use such an encrypted state, because it seems to me that you have a 1 in 4 chance that you guess which rotations were applied, and so with probably if you have some operation that assuming you decrypt the state, always works. You have at least one in 4 chance that you, well, do something.
Okay, good. Yeah, so you're saying, basically, it seems that like I have like a 1 in 4 probability of just outputting psi itself, and so that seems like it's not encrypted, right? Is that essentially what you're saying?
Yeah.
With 1 in 4, with a quarter probability, actually the state's not encrypted at all. Yeah. So I guess the intuition for this even comes from just like the classical one-time pad setting, right? It's the same there, right? Like with the classical one-time pad, with probability 1/2, I just don't even flip the bit, right? But still, information theoretically, you can see that like the bit that you receive is, no matter what bit I started with, the bit that you receive is really just a uniformly random bit. Like, you know, there's whatever bit I receive, there's 1/2 probability that that's the bit that you encrypted, and there's 1/2 probability that you encrypted the other bit and just like flipped it, right? It's really, there's really no information left in. Let me say that when you get the ciphertext, there's like an equal probability that that came from a 0 and it came from 1, so all of that information is gone.
Well, maybe the difference that makes it seem worse is that here we have this whole sphere of states, so, well, infinitely many, but let's say that just many states, and you know that this is one of these 4.
I see, yeah. Yeah, so I guess the best intuition that I was trying to give for that is exactly this kind of like this mixture argument. To see like formally why this is secure, I would have to then like define kind of mixed states and just like go through the math to see that actually no matter what state I started with, like there's no information left in it. But I guess it's the same intuition from the classical setting.
Okay,
yeah.
Thank you.
Yeah, I wonder that in the last row, I think that this is just a single qubit wire and not the tensor product.
So you do need the tensor product here. So if I just multiply all these together, then I'm really only just applying them on a single qubit, right? But here I mean that psi here is an n qubit state. So psi is like a tensor of it's supported on a tensor of n Hilbert spaces. Yeah.
So I think that referring to that question, why we just have two bits here to encrypt, I think that one way to look at it is that what conveys the information in a sense, what corresponds to the ordinal bit, is the states cat0, cat1, and the R will obfuscate whether it's cat0 and cat1, and the S will obfuscate the relative phase, so to say.
Yeah.
Is it correct?
Yeah, that's exactly the intuition, right? Like if you look at it the right way, you'll see that there's really 2 parameters to hide, and each bit is hiding one of those 2. Yeah. Exactly, and one of them is the relative phase. Okay.
In this one-time part, when you decrypt, can you first, for example, decrypt first bit and then the second one, or do I have to decrypt all at once?
Oh, yeah, good question. No, you can encrypt bitwise or qubit-wise, right? So I can, if I have if I just have R1 and S1, I can decrypt the first qubit and just leave the rest encrypted. Yeah, that's true. Okay, so the next building block we need is this notion of a universal gate set, right? So recall that our ultimate goal is to do this like blind delegation of quantum computation. And so really the client will be asking the server to compute for them some arbitrary, let's say, n-qubit unitary. Okay? So to make the task easier for us, our first goal will be to write this unitary, at least approximately, as a sequence of just, let's say, really simple operations. Let's say just 1 and 2 qubit gates from some very small set. Okay, so if I can decompose an arbitrary U into just a couple of like a sequence of really simple operations, then I can just kind of deal with those operations themselves. And so again, this is I think something even Giulio mentioned on Wednesday, that there exist these simple universal gate sets. And I'm also not going to like really give a full proof of of the universality of a particular gate set, but I'll at least try to give like a little bit more intuition about how to derive it. So really I'll just say that I'll just like kind of assert a series of 3 claims. And these are claims that if you're interested in, you can look up in like a reference like Nielsen and Trong to see how they're proven. But the first claim is that I can take any unitary U, which in general is just this like, 2 to the n by 2 to the n matrix, this massive matrix, right? And I can write it as a series of single qubit rotations, so these like 2-level rotations, and CNOT gates, where CNOT is this 2-qubit gate, it's like a 4 by 4 matrix that has the following behavior. It just maps like a bit xy, or basis state xy to x XOR y. So CNOT just basically like is the reversible implementation of the XOR operation. Okay. So to prove this first claim, it's essentially like you just prove it by linear algebra. You say that I can basically build up any 2 to the n by 2 to the n unitary using CNOTs, which kind of like permute some basis vectors, as well as just like single qubit rotation. So like these 2 by 2 matrices. So I can kind of like iteratively build up any matrix by interleaving these operations. But if you want to see a proof, again, you can go to Nielsen and Trong. But this is really nice because CNOT is a particularly simple 2-qubit gate, and now I can only care about single qubit gates, okay, to complete my universal gate set. And any single qubit rotation, the second claim is that any single qubit rotation can be written as a series of one of 2 gates, or a series of 2 gates. So one is the Hadamard gate, and the Hadamard gate is a 100-degree rotation around kind of this axis in between x and z, which I'll sometimes just call the x plus z axis. And so in particular, as we've seen, the Hadamard gate kind of does a basis change between like the standard basis and the Hadamard basis. So it maps like 0 to plus and plus to 0, and it maps 1 to minus, minus to 1, right? And once I have the Hadamard gate, the only other rotation I need is actually something called the T gate, which is just a 45-degree rotation around the z-axis. Okay. So if you recall, the phase flip was a kind of a 180-degree rotation. And here I'm just rotating 45 degrees. So I just take the plus state and move it somewhere here, right? And I take the plus I state and move it somewhere here. Okay. So again, I'm not going to claim this, but it turns out that like once you just have these two, there's plenty of choices you can make, but once you have these 2 rotations, the H and T, I can use those 2 rotations to construct any rotation I want of the block sphere, at least up to some approximation error. And then once we have that, a really nice theorem due to Solovay and Kataev says that actually this approximation is efficient in the sense that I can approximate any single qubit rotation up to epsilon error by using only log 1 over epsilon invocations of the Hadamard and T gate. So meaning I can get exponentially close to the rotation I want by using only polynomial number of rotations. Okay. And again, a good reference for the proofs of this is in the textbook by Nielsen and Trong. Good. So this is our universal gate set. Okay, CNOT, H, and T. Okay. Now, before I actually move on to the blind delegation protocol, there will be another really important class of, yeah?
Is a Hadamard gate, can you replace that with a Z and an X gate and it'll be exactly the same in a quantum circuit?
Can I replace with, so it's like I think it's like a Z plus X, not like a Z times X is actually the Y rotation. But I believe you can write the Hadamard gate as with like this z plus x. So.
Oh, okay.
But that's not so. So in that sense, like it's not like you can just. I can't just. You know, I can't just like keep applying just z and x gates and somehow end up with a Hadamard gate.
Oh.
Yeah, I have to take like a combination of them. Yeah.
Okay.
Does that make
Thanks.
sense? Okay. Good. Okay, so the really another like kind of class of quantum gates that I'll have to introduce you to is something called the Clifford gates. And this will be really important for the scheme. So let's recall what we know so far, which is this quantum one-time pad, you know, how to encrypt quantum states using, again, these Pauli rotations, this x and z rotations, right? Now, the definition, so the way to define the Clifford gate is using like group theoretic terminology. So, you know, in fact, you can define a group generated by these Pauli rotations, and then you can ask, you know, well, the definition of what the Clifford group is technically the normalizer of this Pauli group. But for us, what, you know, we care about the implication of this statement, which is the following. It says that for any Clifford gate C, okay, if I apply a Pauli and then the Clifford, this is just the same thing as first applying the Clifford and then applying a different Pauli. So, you know, this notion of a normalizer basically means that I can commute Cliffords past Pauli gates up to a change in the Pauli gate itself, okay? And so why do we care so much about this relation? Well, we're going to be dealing with encrypted quantum states, right? So, you know, for example, we're going to have a one-time pad encrypted quantum state, you know, say the server has this, and the server is going to be wanting to, you know, apply computation to the encrypted states. So if the server, if all they want to do is apply a Clifford gate to the encrypted state, well, that's good news because they can just directly apply the Clifford to the one-time pad encrypted state, and what they end up with is the Clifford applied to the state itself, so that, you know, the computation actually happened, and the state remains, you know, one-time pad encrypted, and all you have to do is really update the one-time pad keys. Okay, so just in words, Clifford gates are quantum computations that can be applied directly to encrypted quantum states, and all we have to do is kind of update the one-time pad key. Okay, so in some sense, Clifford, the quantum one-time pad is a Clifford homomorphic encryption scheme. This is like a rough analogy is the fact that you know, the classical one-time pad is a linearly homomorphic encryption scheme over F2, right? Good. So how many quantum gates are actually Cliffords, right? Like how far can we get with just Clifford computations? Well, let's figure that out. So recall our universal gate set. So this is just a calculation that I won't really go through, but you can check that C0 is a Clifford gate, right? So I can check that if I try to commute a C0 gate past a Pauli, then the result is, again, that the Pauli kind of just gets updated, okay? So I can pretty much just commute the C0 past, okay? I can check that the Hadamard gate satisfies the same property, right? So I can, oh, yeah.
Sorry, so the polys get updated just with a phase, or?
By updated, I mean like R and S, which define the, you know, R and S define, you know, which qubits like the X and Z rotations are applied to, right? And so that might change, like R and S might change to some R prime, S prime. So I might be like changing like which Pauli rotations are applied to which qubits, but at the end of the day, it's only Pauli rotations that are applied. If that makes sense.
Thanks.
Yeah. Who exactly keeps track of the update? Because supposedly the Clifford is applied by whoever the computation is sent to, but it doesn't have the key. So
we'll get to that. This is just kind of the setup, and then we'll see actually how the protocol works. All right, so we'll get to that. Okay. Okay, so I was just explaining that also Hadamard is actually a Clifford. And for single qubit rotations, basically the way to check if something is Clifford or not is whether it just like, whether if all it's doing is kind of permuting the Pauli eigenstates, right? So the Pauli eigenstates are 0, 1, plus, minus, plus I, minus I. And you can check that the Hadamard, all the Hadamard gate is doing is just permuting them around, right? I swap plus and 0, minus and 1, minus I, plus I. Which is basically telling me that when I apply the Hadamard gate, I'm just kind of like relabeling the Pauli eigenstates, okay? Good. Unfortunately, our final gate that we care about, the T gate, is not Clifford. And I mean, this is for a fundamental reason. It turns out that all Clifford operations if I take a quantum computation with only Clifford operations, that's something that can be simulated classically. So simulated efficiently classically. So in order to get to universal quantum computation, it's not a surprise that we'll have to include a non-Clifford gate. And really, the T gate is not Clifford because of this relationship. Since T and Z are both rotations around the Z axis, T and Z commute, and that's okay. The problem is that T does not commute nicely with the X rotation, right? So you can check, I mean, that if I apply a T, let's say I start with the plus state, I apply a T and then a plus, or a T and then an X, I kind of end up over here. So in order to get back here, instead of just applying X and T, I'll have to first apply like a T squared operation and then apply an X and then apply a T. Okay, so you can write this out for yourself as well. But this is just saying that the T gate does not commute nicely past the X gate. You can kind of force it to commute past the X gate, but then you'll pick up this error of T squared. So I will write this as like, if I take a T gate and try to commute it past the X to the R, Z to the S, what I'll end up with is an expression that looks like this. And now let me define T squared. I'm going to give T squared its own name, which is P, or otherwise known as the phase gate. Again, remember that T was a 45-degree rotation, so P is a 90-degree rotation. So for example, from X to plus I. And so this relation is telling me that if I try to commute T past the one-time pad, I'm going to pick up what I'm going to call a phase error. Okay, there's this like P to the R, where this P gets applied only if R was equal to 1. Okay. P is called the phase gate. Yeah. Okay. Oh, good.
Yeah.
No.
So the question is about where we have n qubits and where we have 1 qubit gate.
Yeah.
So how this formula maps to the n qubit n wires of n qubits?
No. It's a good question. I was actually being quite unclear about this. So in this expression, I'm imagining that these are just single qubits. So R and S are just a single bit. Okay, and T is just a single qubit rotation. Yeah. So yeah, this is for a single qubit. Also, this is for a single qubit, and this is for 2 qubits, the C-naught relation. Yeah. All right. So, okay. I mean, this is basically what I wanted to start with in terms of background, and just to recap. So we've seen how to encrypt quantum states. So again, I could be either. I could be either referring to, say, like a single qubit psi, or say an n qubit state psi, and if it's n qubits, I'm extending R and S to be n bit strings. We've seen this universal gate set C0, H, and T. C0 and H are really nice Clifford gates. And again, the key property of the Clifford gate is that I can kind of, commute it past a Pauli, and all I have to do is update what I will call these Pauli keys. Okay. And just for a piece of notation that will be useful very shortly, for any Clifford C, I will define a function f sub c that does this update. Okay, so it takes as input the classical strings R and S that defined the Pauli on the left here, and it outputs the classical strings R prime and S prime that define the Pauli on the left. And this is just a deterministic, classical, efficiently computable function. Okay. So sometimes I'll just call this like the poly update function, the one-time pad update function, something like that. Okay. And then finally, so okay, what this tells us is that I can take any quantum computation queue. I can first write it as a series of gates. Okay, in particular, I can write it as a series of C0, H, and T gates. And you know, moreover, I can just kind of combine the C0 and H gates into just a Clifford. Like I can just call any combination of C0 and H gates just a Clifford computation. So I will express my computation, Q of X, to be an alternating sequence of Clifford operations and T gates. Okay. So each of these Cliffords just consists of C0 and H gates, and then I'll insert T gates whenever I need to, right? If that makes sense. Good. And then we had this this relation that will end up being extremely important in what follows. Like if I try to force my T gate past the poly one-time pad, I pick up this phase error. And now, okay, hopefully this isn't too confusing, but it's going to be convenient for me to, instead of dealing with T gates, consider T dagger gates. Okay, this will just be a little bit more convenient. And so all the dagger operation is doing is it's just reversing the gate. So instead of considering like 45-degree rotation to the right, I can just consider a 45-degree rotation to the left, and that's the T dagger. Okay. And so what this relation becomes is that if I use T daggers, then I pick up a phase error of a P dagger. Okay, so that's like a 90-degree rotation to the left. Okay.
So here T squared is still not a Clifford gate, right?
Oh, good question. So actually, T squared is a Clifford gate. So P is a Clifford gate, and again, you can kind of check that by noticing that P, okay, it keeps 0 and 1 the same, and it just permutes these four states. It maps plus to plus I to minus, and minus to minus I, and minus I to plus. And just the fact that it's permuting these 6 Pauli eigenstates means that it's a Clifford gate. Okay. Okay. Good. So, yeah. Any questions before I move on? Now I can get into the actual, blind delegation protocol that we've been building up to. All right, so as I promised, I will first show how to reduce blind delegation to a much a more approachable problem, which I will eventually call oblivious BB84 state preparation. Okay. But again, the setup is we have a quantum server on the left, and we have a classical client on the right that has some input X in mind. And they both agree on the description of a quantum computation queue, which again I can write as this alternating sequence of Clifford and T dagger gates. And we want at the end of the protocol the client to receive the output to Q of X. And we want to ensure that the server learns nothing about X during the course of the protocol. So we'll start by essentially having the classical client sample a one-time pad. So let's suppose X is n bits, okay? It'll sample a one-time pad to mask X, okay? And we'll start by just sending the one-time padded version of X to the server. Okay, and the reason I'm writing it this way will become clear soon enough. So the first thing the server does is it takes this classical string and it, writes it, it just views that classical string as a quantum state. Okay, so if I write ket R0 XOR X, this is nothing but the basis state X up to Pauli rotation, Pauli rotations, X rotations determined by the string R0. Okay, and there's no phase rotation, so S0 is actually just the 0 string. But the reason I'm writing the state in this manner is because syntactically I can kind of treat it as a quantum one-time pad encrypted state. Okay, where the one-time pad for now is just defined by this like R, comma 0. Does this make sense? Okay, so all I've done so far is the classical client, a one-time pad encrypts their classical state, and the server kind of receives it. Now, I'm going to retreat my quantum computation to be happening in layers, okay? So each layer is going to consist of a Clifford layer followed by a T-dagger gate, okay? And the first thing the quantum server is going to do is it's just going to, go ahead and just apply the first layer of the circuit to the encrypted state, okay? So, it takes its state size 0 and applies C1 followed by a T-dagger. And we can write out what the result is, right? So first of all, we can realize, again, that this Clifford C1, we can commute it past the one-time pad along as we update the one-time pad keys. And this update can be done kind of simultaneously by the client, right? So the client knows what C1 is. The client knows the original one-time pad because they chose it. So the client can, keep track of what the updated one-time pad keys are, right? They can compute R1, S1. Okay. Next, we can write out what happens if we try to commute the T-dagger past this one-time pad, right? And we have a formula for that, right? So we can go ahead and commute it past, but it's going to pick up a phase error. And let me just say that without loss of generality, I will assume that each of the T-dagger gates in the circuit just gets applied to the first qubit. Okay, I can do that because just permuting, swapping the qubits is in particular a Clifford operation. So I can just assume whenever I apply a T-dagger, it's going to be on the first qubit of the system. So what that means is, based on our formula from before, is that this, commuting this T-dagger past, I can write the state this way, but it picks up this error, this P-dagger, if the first bit of R1 is equal to 1. Okay, so that's what this means, right? So if the first bit of R1 is equal to 1, then I have this P-dagger in front. If not, then I have nothing in front. Okay? So, in order to continue on with this computation, we want to somehow remove this potential P-dagger error. So, one thing I could say is, well, why doesn't the classical client just send over this bit R11 and tell the quantum server which would tell the quantum server whether they have to remove it or not? The problem is R11 is in particular part of the one-time pad. R11 is some bit that could have been derived from R0. So if the classical client just sends this bit to the server, that might be leaking some information about the client's input, right? That's leaking information about the key that they use to hide their input. So for now, I'm going to basically black box a procedure which I'm going to call oblivious phase correction. Okay? So for now, let's assume there's some magic that allows us to do the following. The client will take the first bit of R11. The server will take their state psi1. They will interact using some protocol, which I have yet to describe. Yeah. And then the server will end up with the phase gate applied to psi1, depending on whether the client's input was 0 or 1. Yeah.
But if we're doing this sort of for every T gate, then the client is doing as much work as the server, no? I mean, it's true that the server is quantum and the client is not, but usually you want the client to not do as much work.
Fair enough. So for now, all I care about is that the client is classical. Okay. They can grow, the communication, the computation growth can grow at the size of the circuit for now. But
later you'll be able to remove that?
Later I'll show how to kind of collapse rounds and collapse communication, yeah. But for now, all I care about is the client is classical. Yeah. Okay. Okay, so... yeah.
When the server gets this psi1 and psi1 with this phase, like why are we sure that he cannot recover this R11 from
that's an excellent question. And actually, as I've described this now, there's some, just by looking at, right, you're worried, like just by looking at the output state, they can tell whether the phase gate got applied or not, right? That's the worry. So yes, that's a valid worry. For now, let's pretend that's not an issue, but we will come back and address that issue later. We'll see how to implement this in a way in which they won't be able to do that. Okay, so we'll come back to that. Okay, good. Okay, so assuming that we implement this oblivious phase appropriately, this phase kind of cancels out this phase dagger. And the server ends up with a one-time padded version of, the result of applying the first layer of the circuit to the input X, okay? So now we just repeat this for each layer, okay? Let's call this state psi1 prime, and let's just have the server do the same thing, like apply the second layer. We can write out what happens. The classical client can update their one-time pad, and they can participate in another execution of this oblivious phase correction to correct this potential phase error. And basically, we'll just repeat this for each layer, yeah?
I don't understand how, so you're saying the second line there for quantum server, in psi1, it computes like a phase with R11. Then how does the client know R11?
Good, so the only thing that, okay, I guess a couple things. The only thing the quantum server is actually physically doing is applying this T dagger C1 to phi 0. That's the only thing they physically do, and I'm just like writing, mathematically, I'm just writing the state like this. The client, so the client knows what R0 and S0 are, right? And they also know what the Clifford C1 is. And so, like I claimed earlier that like there's an efficient way to like perform, if you know what the one-time pad is and you know what the Clifford, I claim that there's basically an efficient way to update the keys. So the clients can just like do this by themselves and kind of just run this function on their end and just like know what R1 and S1 are.
Okay, so we're assuming they know how to do this.
Yeah, so this is, I mean, it's really just kind of a simple classical function, and you can, yeah, if you want to, you can actually go back in the slides and look at what the update rules for CNOT and Hadamard are. Like the update rules themselves are quite simple, and then you can just like stitch them together to show that you can do this computation efficiently. Yeah. Okay. Yeah, so basically we'll just repeat this for each layer of the circuit. And so once we arrive at the last layer of the circuit, okay, here all the quantum server is doing is applying this final layer of Clifford gates. And what we see is that the final result that they get is, again, a one-time padded version of the entire computation applied to X. Okay, and again, the classical client has kept track of the one-time pad keys this entire time, so the client knows what this one-time pad is. So this final result is just a one-time padded version of the output, and because we're doing kind of classical client delegation, let's assume that Q is such that the output is just a classical string, okay? It's just a classical basis state. So in particular, Z rotations applied to a classical standard basis state are completely meaningless. So I can write this state as literally just, the output masked with the classical part of the one-time pad, R sub t, and I can have the quantum server return this classical string back to the client. And again, the client knows what RT is, so they can just like unmask this padded version of the output to recover the output. Okay. Good. This is the general template here. Yeah.
So for a question, how efficient is to put a general like quantum circuit? Like for example, I guess no one would write the circuit as a Clifford gate and a T gate. Is it efficient to take a random normal circuit and make it in this form?
Yeah, good question. I mean, so if I just take some computation I care about, you're pointing out that there probably is a significant overhead in first writing that circuit, like decomposing it into this. So that's probably true, and it's not something I'm going to address in this talk. I mean, this is just going to be basically a feasibility result to say that you can do this, and then later you can try to optimize the overheads and so on. Yeah.
Thank you.
Yeah, good. So you're asking like why are we using S at all? Because like for example, this first message just uses R and the last message just uses R, and that's because those messages are classical. But the intermediate states of the computation, so like psi1 prime and psi2 prime, these will be one-time, like quantum one-time padded versions of a quantum state. So even though the computation is starting in a classical bit string and ending in a classical bit string, potentially all of the intermediate computations along the way, or the intermediate states of the computation along the way, will be quantum states. And so we need those to be kind of fully quantum one-time padded. And that's basically ensured by, this update function, even though S0 might start as a 0 string. For example, this S1 might not be 0, right, depending on which operations we're applying. And so we kind of automatically get kind of like non-trivial S strings by doing that. Yeah.
Excuse me? What if Q contains measurements?
Yeah, good. So, so for now, yeah, you're right. I'm just imagining Q as just a unitary, and it maps a classical basis state to classical basis state. I think as Julio mentioned, if Q has measurements, we can always push the measurements to the end. And that just uses, the way to push measurements to the end is to introduce an auxiliary qubit and just apply like a C0 gate. So then I can write Q as a unitary. But then in my output, I'll only, I've introduced all these ancillary qubits, and just to get the output, I just basically trace those out, and I will only look at the part of the output I care about. And so even though there's actually some measurement going on, I can just measure the part of the output I care about, and that kind of collapses to a classical string. Yeah.
Thank you.
Okay. All right. Okay. So this is the basic template, and so basically the main character now is going to be this idea of an oblivious phase correction, right? This is kind of the part of the protocol that I haven't really specified how to do, which again is where the server inputs a state psi, the client inputs a bit r, and the server should end up with, if r equals 0, just the same state they input, or if r equals 1, a phase gate applied to that state. And to be clear, the correctness is specified here. The security is that by interacting in this protocol, we don't want the server to learn any information, or at least no more than negligible information about the client's bit r. So, right, if the client's bit was just something random, it remains, from the server's view, completely random after this protocol. So that's the only security requirement that we care about. So, okay, so now for some history, this template that I presented on the last slide was first developed by Andrew Childs in 2001. I guess actually pretty soon after the quantum one-time pad came out. So Andrew Childs, ran into this issue of this oblivious phase correction, and he said, okay, why don't I just come up with a protocol for implementing oblivious phase correction using quantum communication, even two-way quantum communication, so the server sends some qubits to the client, and the client responds. But the way he did it was so that quantum communication was extremely simple in some sense. The server only has to send maybe some single qubits to the client. The client does some really simple quantum operation and returns the result to the server. So the end result is not a classical client delegation protocol, but it does say that a client can delegate an arbitrary quantum computation to the server while only having to perform, very elementary, simple quantum operations themselves. Okay, so it's still kind of progress towards what we want, which is delegation, right? Okay, so in 2015, Broadbent improved the protocol to show that it actually only requires one-way quantum communication. So to implement this oblivious phase correction, it actually suffices for the client to send single qubit states to the server, and that's all. And this is actually what I'm going to spend the next few minutes talking about. But I'll just mention that finally in 2017, Urmila Mahadev finally introduced the techniques, okay, that allow us to completely dequantize the protocol. So replace that one-way quantum communication with purely classical communication. And this, again, is what we're going to see later. Okay? Okay, good. So how are we going to implement this oblivious phase correction? So here's the idea. Recall that if I apply a phase gate to a single qubit state, we pick up a phase of I. Okay, so we basically add I to, or we incorporate I into the one state here. So this is what a phase gate does. So in order to implement phase gate, I could literally just apply the phase gate to my state. But there's another way to do it, which kind of comes from this way of applying gates comes to us basically from literature on fault-tolerant quantum computation. And sometimes it's called a magic state-based implementation. So the idea is that instead of just directly applying the phase gate to psi, what I'll do instead is I'll first prepare a resource state. Okay, so suppose I just prepare this resource state, which is the plus I state. And then I take my state psi and my resource state, and I apply a C0 gate from psi to the resource state. So I can write out explicitly what I get if I do that. You can just check that the C0 from this state to this state will produce this 2-qubit state. And then what I'll do is just I'll measure the second qubit in the standard basis to produce a single bit outcome m. Okay? And you can check that if m is equal to 0, well, let's check it. I mean, if the second qubit is 0, then the first qubit has collapsed to alpha 0 plus I beta 1. That's good. That's exactly the phase gate applied to our input state. On the other hand, if m is equal to 1, you can check that the resulting qubit is I alpha 0 plus beta 1. Okay, up to a global phase, I just divide by I, and I'll see that I get alpha 0 minus alpha beta 1. And I can write this as just a z flip applied to alpha 0 plus I beta 1, right? The z just adds the phase of negative 1. So compactly, the result of you're performing this operation is that I actually do end up with a phase gate applied to psi up to some potential phase flip. And whether I apply the phase flip or not depends on the measurement I got from measuring the second qubit, okay? But in some sense, this is good enough for us. We don't care if we pick up like z or x flips, right? Because we can just incorporate that into the one-time pad, okay? So this is essentially as good as applying a phase gate to the state. And then the poly error is not a big deal, okay? But let's go through the following exercise. What happens if instead of starting with 0 plus I1, I actually just started with the plus state, but I run the same procedure, right? So you can check that if I apply C0 to psi in the plus state, okay, you can write out what state you get. You can measure the second qubit. And again, you can check, like if the second bit is 0, then my state just collapses to my original state, alpha 0 plus beta 1. And the same thing if m is equal to 1. So the point is that if I had started with a different resource state, if I had just started with the plus state, and I apply the same procedure, my state remains the same. I haven't applied the phase gate at all, right? So you can note that the only difference between these two procedures is this resource state that I start with, okay? But at the end, I've succeeded in either applying the phase gate or not, okay? So essentially what this shows is that in order to apply the oblivious phase correction, it suffices to perform what I will call an oblivious state preparation, right? So if the client can somehow send to the server, this is the idea of Broadbent's like one-way communication protocol, is that if the client could, based on their input bit R, send to the server either the plus state if r equals 0 or the plus I state if r equals 1, then the server could apply, this procedure from this slide and end up with, if r equals 0, just psi, or if r equals 1, the phase gate applied to psi. Okay, so essentially, I can reduce oblivious phase correction to this oblivious state preparation functionality. And now, just to visualize what's happening here, we can return to the block sphere and note that based on the client's input bit R, we're either preparing, or we're supposed to either prepare the plus state or the plus I state on the server side. Okay? Okay. Good. So I can write this, again, compactly as just like, if r equals 0, it's just the plus state. If r equals 1, it's the phase applied to the plus state, which is plus I. Okay, so finally we're returning to a question from earlier. Now let's address this issue, which I will make very explicit, which is that, as stated, actually no protocol can achieve this security requirement, okay? I want it to be that after this protocol, the server learns, no information, maybe negligible information about the bit r, okay? But this can't possibly be the case. For example, suppose that the server receives their output, which is p to the r times plus state, and they just measure their received state in the plus-minus basis or in the Hadamard basis, okay? If r equals 0, the server will definitely see the plus state, with probability 1. On the other hand, if r is equal to 1, the server will see each of these two possibilities, each with probability 1/2. Okay? So, this certainly gives the server some constant advantage in predicting what this bit r is. In particular, if the server sees the minus state with this measurement, they know for sure that the client's bit r was equal to 1. And this gives them, a way to, this leaks information potentially about the client's input. Remember, we want to keep r completely hidden. Okay. So the way to actually fix this is to allow for this state preparation functionality to potentially flip the phase of the state that the server receives. Okay. So instead of just sending the server either the plus or the plus I state, this oblivious state preparation protocol will potentially, will essentially sample a random bit b, and based on the bit b, either flip the phase of the state or not, okay? And the client will receive, will learn what is this bit b, so the client knows exactly which state the server receives, okay? So here the idea is that, if r equals 0, okay, the server is going to get either the plus or the minus state with equal probability, and that, again, that's just something, that's like the maximally mixed state. And if r equals 1, the server will get either the plus I or the minus I state, and again, that's, from their view, that's a maximally mixed state. So in either way, regardless of whether r equals 0 or r equals 1, the server has no ability to distinguish kind of which state they received. Okay, so this is basically the change we kind of needed to allow for this flexibility in order to possibly be able to achieve the security requirement. And again, the security requirement is the same. Okay, it's just that the server can't guess the bit r. But we can see now that really what this means is that the server just cannot guess which basis their state is prepared in. So in the one case, their state is prepared basically in the x basis. And in the other case, their state is prepared in the y basis. And we just want to ensure that they can't distinguish which of these two cases happened. Okay. So finally, it turns out to be easier to implement this protocol if we don't have to deal with complex phases. So an equivalent task is to actually prepare instead one of the 4 BB84 states. Okay, so suppose that instead we delegate the preparation of the plus, minus, 0 or 1 state, and then we just ask the server to apply a rotation. So they prepare one of these 4 states, and then they apply basically the square root of x rotation, which the server on their own can basically rotate between these two possibilities, right? So the point is that all we have to do is to send to the server one of these 4 BB84 states. If r equals 0, they obtain either the plus or minus state based on the bit b. And if R equals 1, they obtain either the 0 or the 1 state, again, based on the bit B. Okay? And then I can, again, write this succinctly as, the state that comes out on the server side is the Hadamard applied to the bit B, where the Hadamard is applied if R equals 0. Okay. Yeah.
Just a question on the notation here. So when you write this R going into this box, because if I understand correctly, we are not sending the R, right? This is the meaning of this arrow is different, right? We send these quantum states. I'm just asking about the notation. When you write like this R going inside of the box, it's not sent to the other side. It's just
Good. Yeah. So the R is kind of like, again, this is still kind of like a black box that I haven't shown you how to do. So R is a single bit that the client kind of inputs to some protocol that I've yet to describe. And the result of the protocol is to spit out just this quantum state to the server. It doesn't additionally output R.
So these are just the inputs and outputs of the two parties.
Exactly.
Okay.
Exactly.
Want to know. Okay, thank you.
Yeah, these are inputs and outputs of the parties. Yeah. Okay. So just to recap, I mean, the progress that we've made so far is to show that this.
Sorry. Previous slide. So can you just remind us? So this, what we wanted was this P to the R. So ZB P to the R is good for us, right? Mm-hmm. And now you changed it to H1 minus RB. Why are these two the same?
Oh yeah, good. So if I can prepare H1 minus R to the B, which is one of these 4 states, I can just have my server apply a square root of x rotation, which the result of that is to map 0 to minus I and 1 to plus I. And they always apply that rotation no matter what. And then they prepare one of these 4. Yeah. So that's basically the same, just up to a fixed rotation, right? Okay, so far we've seen, basically, that the ability to, I guess I should say, notice that, we've been talking a lot about BB84 state, Wisner encodings, right? That's exactly what these 4 states are, right? 0, 1, plus, and minus. So I'm going to call this protocol an oblivious BB84 state preparation protocol. So we've seen that once we can do that with classical communication, that gives us the ability to do this oblivious phase correction, which then in turn gives us the ability to delegate arbitrary quantum computations in a blind manner. Okay. So I think I can give it start this, get like 10 minutes into this next part, and then arrive at a good stopping point. Okay. So next, our goal is to understand how to implement this oblivious state preparation protocol using just classical communication, okay? And the key cryptographic tool we're going to use to do that is something called a trapdoor claw-free function, okay? So what is this? A trapdoor claw-free function is a pair of injective functions, so f0 and f1, that have the same domain and range. So like the blue is the x domain, orange is the y range. Okay, with the property that for any y in the range, okay, there exists exactly, 1x0, 1x1, such that f0 of x0 equals f1 of x1 equals y, right? So each image point has exactly, one preimage under f0 and f1. So by trapdoor, I mean that there is some gen algorithm that outputs the description of these functions. So like, it's a randomized procedure to generate the description of these functions. And this gen algorithm also outputs a trapdoor, okay? So that, if I have the trapdoor and I'm given an element in the range of these functions, I can determine what were the 2 pre-images, x0 and x1, okay? And then finally, what does claw-free mean? This is the security property. This is really the only security property we care about, which is if I'm given the description of f0 and f1 and I'm a polynomial time machine, it's difficult for me to find any one of these claws. Like a claw is an x0, x1, such that f0 of x0 equals f1 of x1, right? So obviously, by definition, many of these claws exist, but it should be hard for a polynomial time adversary without the trapdoor to find any one of these, okay? Now, one kind of, I'm actually going to technically be dealing with the strengthening of this property of claw freeness, okay? And one way to ensure that my functions are claw free is to instead insist that they satisfy the following dual mode property, okay? And the dual mode property now states that the gen algorithm actually takes as input a single bit r. And if r equals 0, it operates as before, and just outputs this pair of functions that have the same image, right? Whereas if r equals 1, it generates these functions in a slightly different way so that actually their images are disjoint, okay? And my security property that I care about is this thing called mode indistinguishability, which means that my efficient adversary cannot distinguish whether these functions were generated in mode 0 or mode 1, right? And this, if I can show that, then this automatically gives me the claw-free property, right? Because if I could find a claw, then when I'm given f0, f1 generated in mode 0, then I will be able to find a claw. But if they were instead generated in mode 1, then their information theoretically does not exist a claw, okay? So, basically, if these modes are indistinguishable, it must be the case that the adversary cannot find any claws, even in the 0 mode, okay?
If we generate the DTCF in the r equal 1 mode, what does then the trapdoor do?
Good. So the trapdoor will given any y in now this range, the yellow plus red range, it will return the single preimage. Okay. So it'll return like 0, x0 or 1, x1. Yeah.
Another question. So maybe it's incorrect, but can we just think of these claw-free functions as applying a permutation on all the inputs? Like we just take one function and then we inject the function, and then we just permute.
It doesn't necessarily have to be a permutation because like this range could be different than the domain.
Okay.
Right.
Okay. Yeah, thanks.
Okay. Oh, good. Okay. Okay. So yeah, in the last 5 minutes before lunch, I think I can basically give you the protocol for how to do oblivious BB84 state preparation using a dual mode trapdoor claw-free function. The protocol is actually quite simple. So, okay, we have the server on the left, client on the right. And the client will start by just like, the client's input to this protocol, remember, is this bit r. And this bit r determines whether the server's state should, at the end of the protocol, should be a standard basis or a Hadamard basis state. So what the client will do is it'll first sample a DTCF in mode R, and then it will send the description of these functions to the server. What the server will do is it will prepare a uniform superposition over bits and inputs, so domain elements. Okay, and then it will apply this function in superposition. So it'll first prepare this state that it's a sum over all bx and fb of x. It'll just apply this function in uniform superposition, and then it will measure the output register in the standard basis to obtain some output y. Okay, and now there's two cases in which we can kind of understand what's going on, right? In the case in which the mode bit was equal to 0, then this is a 2-to-1 function, and so the remaining state on the server will be in a uniform superposition over two states, some 0x0 and some 1x1. What? Otherwise, if the mode bit was r, then measuring this output collapses the remainder of the state to a single basis state. Right? There's only one preimage of each y. So what the server ends up with is just this kind of classical state b xb. The next step, or the final step really, is to have the server then measure their input register, so I'm calling X register the input register, measure that register in the Hadamard basis, okay? In the case that R equals 0, it's easy to understand what's going on because like this, measuring this state in the Hadamard basis does not affect this first bit at all because they're just classical strings. And so at the end of the protocol, the server obtains just this, this standard basis state B, right? Okay. A little bit more interesting is what happens when the server measures a so-called claw state in the Hadamard basis. So, now let's suppose the server has 0x0 plus 1x1, and they measure the X register in the Hadamard basis. One way to understand what's going on here is to imagine first applying Hadamard gates to this register. Let's say the register is lambda bits. And then measuring that in the standard basis. It's equivalent to see what's going on. So if we just write out what happens when we apply Hadamard gates to this state, we can just write it out. If I apply Hadamard to a computational basis state x0, I get a uniform superposition with a phase defined by the string d. And the same thing for x1. Okay. So I can then write this state. I can factor out d and write this state as a sum over all d, where the first qubit is either -1 to the d dot x0, 0, plus -1 to the d dot x1, 1. So then if I measure my my final register d in the standard basis, you'll see that the remaining state kind of collapses to this single qubit state. Okay, and by factoring out a global phase, we'll see that this state is equal to 0 plus 1 with some phase that depends on d, x0, and x1. Okay? And so I can write this state, again, succinctly. If I measure d here, and in the case that r is equal to 1, the result is that the first qubit collapses to the plus state up to a bit flip, or a phase flip, again, that depends on d, x0, and x1. Okay? So this is good, right? The server's output, in the case that r equals 0, is either the plus or the minus state, so in a Hadamard basis state, whereas the server's output, in the case that r equals 1, is just a standard basis state, either 0 or 1. This is kind of exactly what we wanted. And then to complete the protocol, we need to let the client know what state the server got. So the server can just return everything they measured, y and d. And again, the client can just apply the trap door to y to learn the preimages. Okay. And in the case r equals 1, the client just learns what the bit b was. In the case r equals 0, the client knows d, learns what x0 and x1 are, and can use that information to determine this bit b, which is exactly the bit that determines whether the server's output was the plus or the minus state. Okay. So this is exactly how the protocol works. What we've talked through here is basically the correctness of the protocol. And then what about security? Like, security is extremely easy, actually. It just follows directly from the mode indistinguishability property of the dual mode TCF. The security is that the server gains no information about R, cannot guess what R is. The DTCF mode indistinguishability property says exactly that if you have these two functions, you can't guess what mode they were sampled in. So that's exactly this task of guessing whether R equals 0 or R equals 1. Okay. So I think this is a good time to stop. After lunch, we will see, so basically we've reduced blind delegation now all the way to this kind of task of building a DTCF. And so after lunch, we'll see how to build this from the LWE assumption.